So in previous lecture, we designed a band reject filter by putting a low pass and high pass filter in parallel, in which the cutoff frequency of our high pass filter was greater than the low pass filter. Here I want to show you the transfer function of the circuit, the overall circuit, and then I will show you that why we are saying that we need to have widely separated cutoff frequencies in order to make sure that the cutoff frequency of the overall circuit is equal to the cutoff frequencies of individual low pass and high pass filter. Okay, so now let's focus on the transfer function of the circuit. So our H of S is going to be, let's go back and look at the parallel connection. So we have the low pass filter in parallel with high pass filter. Now remember that because this low pass filter and high pass filter are using op amp in their circuit, they don't have loading effect on each other. So it means that we can consider them as control blocks, and they can be easily added together in order to form the overall system transfer function. And then at the end we have a summing amplifier that we have to multiply the gain that comes from the summing amplifier. So what I have to do here is that I have to add the low pass filter and high pass filter transfer function together and then multiply them by the gain that comes from my summing amplifier. So the parallel means that I have to add the transfer functions and the summing point, which basically means that the result of the parallel is cascaded with the summing point, means that I have to multiply the summing point amplifier by the overall transfer function. Okay, so the transfer function of my low pass filter is equal to x over s plus x, actually minus x, and then the high pass filter is minus s divided by s plus y. Now my gain that comes from the summing amplifier is equal to minus rf divided by ri. What I'm going to do here is that I'll cancel out the negative here and the negative that I have inside this parenthesis. So now let's look at the transfer function after rearranging and bringing these two fractions into common denominator. Okay, so this is going to be my transfer function. Now here in denominator I have xy, which is going to be my cutoff frequency squared, and the coefficient of s is y plus x. Now, if I can assume that my cutoff frequency for low pass and high pass filter are widely separated, which means y is much greater than x, then I can assume that y plus x is very close and similar to y minus x. That's an important conclusion that helps me to say that my cutoff frequencies are equal to the low pass and high pass filter cutoff frequencies. So I can replace this y plus x by y minus x. And again, because y is much greater than x, then this 2s multiplied by x can be ignored. And what I am going to have here is similar to what I have for the standard transfer function of a band reject filter, which is s squared plus omega naught squared divided by s squared plus beta s plus omega naught squared multiplied by the gain. So if I match the coefficient, it means that r divided by rf divided by ri is my gain. Y multiplied by x is my center frequency squared, or omega naught squared, and this y minus x is my beta. So let me write everything in another slide. So based on the transfer function, what I have is that my omega naught squared is equal to x multiplied by y, and my bandwidth is equal to y minus x. And on the other hand, I know that omega naught squared should be equal to the result of multiplying the cutoff frequencies together, and beta should be equal to the difference of the higher cutoff frequency minus the lower one. So omega C2 minus omega C1. So if I look at these two equations, I can say that if I choose my omega C2 to be exactly equal to y and omega C1 as x, then the other equation also satisfies with these numbers. So according to this, my cutoff frequency omega C2 and omega C1 are going to be equal to y and x. Remember that this is exactly the opposite of bandpass filter. In bandpass filter, just to remind you, we ended up having omega C2 equal to x and omega C1 equal to y. So for a bandpass filter, our greater cutoff frequency was equal to the cutoff frequency of low pass, but here the greater cutoff frequency is equal to the cutoff frequency of high pass. So this is something that you should be very careful about. So this is the final conclusion that I have here. Now I want to show you the step that we have to follow in order to design a band reject filter. So here I want to talk about band reject filter design. So the first step is choosing commercially available capacitor for low pass and high pass filter. So the first step is choosing CH and CL, because if you choose your CH, then it's easier to find a resistor value which is the result of calculating in the next step. So you have to choose one of them, either R or C, and based on the equation you have to find a value for the other one. Now it's easier to choose your capacitor value because the capacitor values, the range that you have for capacitors, are limited. So it's easier to choose the capacitor value and then calculate and see what should be the resistor value and provide that value. Okay, so the next step, step 2, is finding RL based on desired omega C1. So I want to refer to the previous slide. Omega C1 is for band reject filter is related to the cutoff frequency of my low pass filter, and the cutoff frequency of the low pass filter is equal to 1 over RL multiplied by CL. So according to this equation, I can calculate my RL. I'm gonna write it here. So RL, in order to find RL, the equation that I need to use is omega C1 equal to the cutoff frequency of my low pass, which is equal to 1 over RL CL. So here I have CL. I've already chose my CL. I know what is the cutoff frequency because I'm designing a filter knowing that I need omega C1 and omega C2 for my circuit. So then the only parameter that I don't know here is RL, so I can find this particular parameter. The next step is finding RH based on omega C2 here. So this time I can say that omega C2 should be equal to Y. So the cutoff frequency of my high pass filter is equal to 1 over RH multiplied by CH. Again, I have my CH. I know what is my desired cutoff frequency, a greater cutoff frequency is, and then I can find my RH here. Okay, and then the last step, or step 4, is choosing our I and our F based on my desired gain. So I have to choose RI or RF, and then I can find the other one based on my desired gain. Now remember that these steps are correct if you can assume that your frequencies are widely separated. So if these are widely separated, then this approach works. Otherwise, you have to use the transfer function that we have here. So you have to use the original transfer function without applying the red simplification. So then you cannot remove this one because your frequencies are not widely separated, and you cannot replace your y plus x by y minus x. So then you have to say, this is my omega naught squared, this is my beta, and you have to solve the equation.